will be able to watch this at your own pace next week on Thursday. So what did we do last time? Last time we went to the derivation of the electric field integral equation, and I've stated that here again. We have the integral of, basically what we have is E incident is equal to negative E scattered, right? There's the equality here, and on the left we have E incident, and on the right we have E scattered, which has this component and this component, a couple of components, right, depending on how we moved the derivative operators. I don't know if you remember, but last time we moved the derivative operators from the double derivative onto the Green's function, and we moved them onto the testing and source functions. So maybe if we just go back in and take a look quickly what we derived last time. So the integral equation starts with the tangential electric field going to 0, the PEC boundary condition, and we have the tangential components of the incident field are equal to negative the tangential components of the scattered field. The scattered field is expressed as a spatial convolution of the Green's function and the induced surface current density. In this expression, the only unknown is the current density under the integral, which makes this an integral equation. To solve it, we're going to expand the current density in terms of a weighted superposition of vector basis functions, and we're going to define the dyadic Green's function as the following operations, and we're going to substitute these two expressions into the integral in the integrand in our integral equation. And what we get here is the following expression, which is E incident equal to negative E scattered. These two derivatives here, though, we said cause problems if we have to differentiate the Green's function twice. So what we're going to do next is we're going to rearrange the terms, the derivatives, so that they operate on the functions, or the testing and basis functions. Before we do that, though, we have to form the integral equation by taking the functional dot product of the testing function with both sides of the equation and integrate over the domain of the testing function. And if we rearrange by pulling out the summation and the unknown coefficients, we end up with the EFIE here. This EFIE, though, has the derivatives operating on the Green's function, and they're both observation coordinate derivatives. What we're going to do, or what we did, was we rewrote this term in brackets, or under the red bracket, as the following expression. And what we did was move these two derivatives onto the basis functions and the testing functions. And in order to do that, we had to do two things. We had to re-express these two derivatives as divergences, and we had to change one of these derivatives to a derivative on the prime coordinates, right? And we did that all by using one expression. This is how we transform one derivative from unprime coordinates to prime coordinates. We pick up a negative sign. And to convert into divergences, we use these expressions here. So this expression has a divergence in it. Here's one here. So we want to use this divergence because J represents the basis functions. And we want to differentiate those. And these two terms we find, and we use divergence theorems and so forth to eliminate one of the other terms. All right? Okay. And we ended up, after all that, here. So we have this integral equation, this EFIE. On the left, we have the voltage vector V, and it's a function of the index M. So there are M observation edges. Remember, these basis functions are placed on edges. So for example, whenever you compute an element of this matrix or this vector, of course, you don't compute that vector, you solve for it. And this vector, you consider either one or two edges. If it has an index M, then it's only an observation edge. The observation edge is here, for example. This is edge M, the mth edge. And whenever you compute the left-hand side here, what you're computing is the observation, the electric field, E incident, as a function of R. And here's this position vector R, so we're calculating E incident at that point. And we are multiplying that, or taking the dot product, with this Fm here, which is this set of two triangles. All right? And then we integrate over those two triangles. So we take this function here, E incident, this one. We evaluate it at many different R's. As a matter of fact, it continuously varying over all of this triangle's area, both these areas. And we evaluate this integral. All right? All right. For the impedance matrix, we have two edges. We have the observation edge. We have the source edge, edge N. All right. And we have to do the same thing. We have to calculate these quantities, take the dot product of these two vectors. And remember these two vectors here, Fm and Fn, let's say F itself could be M or N, is equal to Ln over 2An, could be plus or minus, and it's rho plus or minus, right? I suppose since we wrote N, we should just say N, and this is R. All right, and rho N's are defined here. So we have this R, this vector here that points to the observation point, and we have this vector here that points to the free vertex. We figured out how to calculate the free vertices earlier in an earlier lecture, and we subtract the two and we get this vector here, which is rho. All right, so you'll have practice doing that in your homework. So if we had to integrate, for example, for the impedance matrix, you have to integrate over both of these two triangles. So there's 4 triangles total. Or the voltage vector, we have to integrate over 2 triangles, right? So how do we do that? We'll show how to do that. But in order to do that, we also have to integrate over the domain of Fm and integrate over the domain of Fn. Fn's domain is both of these triangles. Fm's domain is both of these triangles. So we have to learn how to integrate over triangular polygonal supports or triangular domains. And the way we do that is an approach called Gaussian quadrature integration. So this slide shows how to perform the integration over a triangular domain, triangle T, and some function that depends on a position vector R, shown in red here, and is a function, and then we integrate over the entire area of that triangle. All right? How do we do that? So the way we do that is we use the following thing. It's called Gaussian quadrature integration. Somebody has figured this out before in these papers, or in this seminal paper. And first thing we need to understand is how we can express this position vector R, or any point within this triangle T, in terms of a weighted combination of the vertex, the vectors that point to the vertices. For example, any position vector R here can be written as 3 scalar coefficients, alpha, beta, gamma, that weight vector v1, v2, and v3. And v1, v2, and v3 are position vectors to the free, or to all the vertices, vertex 1, 2, and 3 of the triangle. All right? Good. All right. So, and then by the process of Gaussian quadrature numerical integration, any function f of x, y over a triangular domain can be calculated using the following formula. We take the following formula is, we have the area of the triangle, A. We multiply that by the summation of the product of the weights and the function evaluated at the alpha, beta, gamma. Where did those come from? These are pre-calculated and provided in this paper. For example, here's a 3-point rule. So I goes from I equal to 1 up to 3. And we add up three product terms. Here's the W column, which is the weights. And here are the alphas, the betas, and the gammas. So to calculate an integral over triangular domain, we first evaluate the function that we're trying to integrate at alpha, beta, gamma, I. So at 3 points, right? And to do that, we take the position vector, we multiply by alpha, beta, and gamma, we take the free vertices, the vertex vectors, we multiply them by alpha, beta, gamma, and we evaluate our function at that R. All right? Then we multiply by the weight associated with that row, with that point, called a Gaussian quadrature integration point. All right? So the integration effectively gets transformed into a summation, which has a well-known construction. So is it clear? Here, for example, a 1-point rule. 1-point rule means that alpha, beta, and gamma we multiply by 1/3, which means it puts us right at the center of the triangle by the formula for the centroid of a triangle. Right? It's the exact same formula. You take the 3 vertices and you multiply them by 1/3, and you sum them up. You get the center of the triangle. And then the weight coefficient is just 1. So we evaluate the function itself at the center of the triangle using this alpha, beta, gamma, and these 3 vertex vectors. And then we multiply that by the weight, which is 1, right? So it's basically just an evaluation of the function at the center of the triangle. A 3-point rule, on the other hand, we have 3 points. So we would have 1 point here, for example, 1 point there, for example, and 1 point there, for example. And we evaluate the function at each of those 3 points by multiplying the associated alpha, beta, and gamma for that point by the 3 vertices, V1, V2, and V3. That'll put us right at a Gaussian point. We evaluate our function at that point. We multiply by the corresponding weight. And then we add up the same calculation for all 3 of the Gaussian integration points, yeah?
What is f right now? So we know that
F is some function.
Where is the r? Based on the alpha, beta, and gamma?
Yes. So normally you'd have to, go ahead.
Yeah, so f should be a function of those, which is.
Yeah, so normally we integrate this function f over the entire domain of T, over the entire triangle, right? But instead of doing that integration, we can do that integration by representing it as a summation of 3 terms, 7 terms, 1 term, right? Depending on what point rule you pick. By multiplying this weighting coefficient by the function f that we're trying to integrate, evaluated at the r, which is represented in this way, right? So you sum 3 of these r's if you're using a 3-point rule, evaluate the function at those 3 r's, where the alpha, beta, and gamma define each r, and multiply by the weight associated with that alpha, beta, and gamma from each row of these rules.
So basically, we scan the entire surface point by point.
No, this integration over a continuous domain, a continuous integration over that whole domain gets transformed into a summation of discrete points evaluated and weighted. Yeah, it's pretty cool. If you go to the mathematical theory behind Gaussian quadrature integration, then you'll see that it's really cool. Okay, good. So now all the integrations that we see where we have to integrate over basis functions involving 2 triangles that support each of these basis functions can be done by this integration into summation rule. Now don't forget, you have to weight your summation by the area of the triangle, area of triangle T, okay? And we'll see some formulas. So here's a MATLAB program that I wrote that allows you to get a quadrature rule table based on the number of points you want. So that more points you use in the integration or in the summation becomes more accurate. So here's just those tables represented in terms of MATLAB matrices. Yeah? Okay. So let's see how to calculate these. So we derived the impedance matrix in the following expression here. We move the derivatives onto the testing and the basis functions. And now we can calculate the divergence. We need the divergence of f and the divergence of fn and fm. And these are the divergences here, right? We calculated these when we first introduced the basis functions being divergence conforming. And we can plug in these 2 expressions for these 2 terms here. So sometimes this term is referred to as the vector potential term, and this one is the scalar potential term, because this is a linearly varying vector that deals with current. And because we're taking the divergence of this current, right? Fn represents current and Fm represents a testing function, but it's the same as a basis function. When we take the divergence of current, then we get charge, right? Time varying charge by the divergence or the continuity, charge continuity equation. Therefore, this is an integration of charge. So this is like a scalar potential. This is like a vector potential, all right? Okay, good. So plug in these divergences there, and we get the following expressions. So if you look here, this divergence is divergence of Fm becomes Lm over An minus, right? So Lm over An minus if you're in the minus triangle. If you're in the plus triangle, then you have a minus sign, all right? So these are constants, they will come out of the integral. So all you'll have left is 1 over k squared and j omega mu multiplied that. And that becomes j over omega epsilon. Because 1 over k squared times j omega mu, what does that equal to? Well, that's j omega mu 1 over omega squared mu epsilon. And that, these j's, or the j is there, right? So you get j. The 1 omega here cancels, so you get an omega. And then the mu cancels, you get epsilon. All right, now why are these signs here in red? First, let me explain what all these are. So that integration over 4 triangles, right? We break it into, and we know how to integrate over one triangular domain. So we use the Gaussian quadrature to integrate over a single triangle. We have to break these integrations over both these triangles into pairs of triangles because we know how to integrate over triangular domain. All right? So then there are 4 combinations of pairs of triangles. Both of the left sides, then the right and left, then the left and right, and then both right. Right? So there are 4 terms if you want to do the full integration of the basis function and the testing function, right? To calculate ZMN. So ZMN then is calculated by summing these 4 integrations, right? Okay. Now, so why is there minus here, plus, plus, minus? Well, if you look here, this one has both left sides, so it's a minus triangle, minus triangle. Remember, in the basis function definitions, we have one triangle is defined as the minus triangle, one is the plus. The left side here is minus triangle, this one's the plus, right? So, and if you look at the divergence formulae, what you'll find is that there's a minus sign whenever you're in the plus triangle. So if they're both plus triangles, then these 2 negatives will cancel. If they're both minus triangles, then there is no minus sign. Only when they're different, when it's a plus and a minus or a minus and a plus, do you pick up a minus sign. So if you look at these formula, there are 2 plus signs only when these are different, right? When they're the same, then that's a minus sign because we absorbed a minus from somewhere else, all right? So be cognizant of that. Very important that you consider that, yeah? Okay, so we've reduced the integrations here. Now we still have continuous integrations over triangular domains now. Instead of saying that this is the integration over Fm, the domain of Fm, or integration over the domain of Fn, what we have instead is integration over the triangle Tm minus and integration over triangle Tn minus, yeah? Okay, great. So what do? Now we have to integrate that. Well, let's use our Gaussian quadrature rules. So before, we have these as continuous integration symbols here. We're integrating, right? Integration, integration. We're going to now use Gaussian quadrature to convert them into summations, all right? So all we do is use our Gaussian quadrature rule. An endpoint rule could be 1, 3, 7, or 5, or whatever rule you want to use. Endpoint rule. We have to sum over the source and the observation because it's integration over Tn and Tm, right? And Q here is going to represent the Gaussian quadrature point index for the source, and P represents the Gaussian quadrature point index for the observation. All right? And RPQ here is defined down here, which is the square root, it's the distance formula between the qth Gaussian quadrature integration point. So you choose alpha, beta, and gamma multiplied by the 3 vertices of the source triangle, and that puts you at some point within the triangle. That has an XYZ coordinate, and you use that as XQ, YQ, ZQ. And you do the same thing for the observation, which is the pth observation point, and you get XP, YP, ZP. Then you find the distance between those two. That is your R, right? That's the distance between the source and observation. That matters in the Green's function, E to the minus JK RPQ over RPQ. And we sum over all of these in order to calculate the integrations that are involved in the impedance matrix, right? Okay, good. So here's some code to do that. So we have first a basis function shown here. It's the nth edge, for example. And here I'm showing a figure that has the free vertex vector coming from some coordinate origin off in the distance. We have the minus vertex and the plus vertex, right? And we have 1, 2, 3 points in the minus triangle and 1, 2, 3 points in the plus triangle. So point number 1, for example, is pointed to by RP1 minus. All right? Because it's the first integration point, the observation point P, and the minus side of the triangle. RP1 minus, remember, is alpha 1 V1, let's call it V1 minus, I suppose, plus beta 1 V2 minus plus gamma 1 V3 minus. Yeah? All right, good. Okay, and then there are RP2, RP3, RP1 plus, RP2 plus, RP3 plus, right? Good. And you'll notice the direction of the vectors start from this free vertex on the minus side, goes to the point. And on the plus side, it goes from the point to the free vertex. So the current flows continuously across the edge. Okay, good. So how do we do that in code? So first thing we do is use that function I showed you earlier to get the Gaussian quadrature rule, get the table that has the alpha, beta, gamma, and the W. All right? Then we loop over the testing functions first. So from m equal to 1 to the number of edges. And the first thing we do is we get these vectors here. So the points, triangle, plus. Okay, so we get the plus vertices, right? Which is on this side, RP1. We need the vertices first, sorry. The vertexes, right? Of the plus triangle. So we go to the P matrix, which has the XYZ coordinates of each point. And we ask it to give us all 3 rows. So that's what this means. All 3 rows of the P matrix, so the X, Y, and Z coordinates of the triangles. So then you go to the T matrix and you use the first row of the T matrix gives you the first point of the vertex, right? Okay, so here's a triangle, has 1, 2, 3 vertices. The T matrix, let's call it 1, 2, and 3, right? The T matrix is going to have, so let me write it like this. The T matrix is going to have P1, P2, P3, and it's going to have a matrix like this. So let's call this 1, 2, and 3. And then there's more quantities, right? So the T matrix has the vertex labels, right? But then you have to go into the P matrix, which has X, Y, and Z for each point. So this is point 1, 2, and 3, right? So this will be some X, Y, and Z coordinates. This one, this one, this one. So if you want the X, Y, Z coordinates of the first vertex, then you have to go into the T matrix, tell it which triangle it is, and take the first row, and then you use that as the column index and get all 3 of these quantities, right? Okay. So that's what we're doing here. The 3 vertices there, and the 3 vertices of the minus triangle, right? So we tell it what edge we're working on, which is edge M, and we use the triangle minus vector. We tell it which edge it is. It tells us what the triangle number is associated with that edge. It'll tell us what triangle number this is. Say it's 3 and this is 2, right? And do the same thing for the plus, all right? Okay, then, okay, this might be hard to explain, but this is a fast way to calculate all of these RP vectors simultaneous, all right? What do? So we have repmat, which means repeat matrix. We take all rows column 1 of our quadrature rule table, that's the alphas, all right? And we repeat that. So all rows column 1 of our, let's say we're doing a 3-point rule. All rows column 1 is all of our alphas for all of the points, right? Okay. So we get all of the alphas. And oh man, well, let me clear this now. Okay, good. We get all of the alphas and we repeat that into a 3x3 matrix. All right. Okay. Then we transpose it and we multiply. So we repeat it as a 1/3 and then we transpose it here. Dot transpose means do not do conjugation when you do the transpose. So make sure you add this dot here if you're going to use the transpose operator. My goodness, transpose operator, because then you'll avoid having bugs in your code with conjugation. And you multiply that by the free vertex and you repeat that matrix by 1 times the number of the quadrature rule, which is a 3-point rule. So what are we doing there? We're taking all of the points, all the Gaussian vector points here, which for the free vertex 1. So we're taking the V1 and we're multiplying it by all the alphas in one matrix multiplication operation. So you have to go through some examples of this and understand it and prove it to yourself, all right? And then we do the betas times V2 and the gammas times V3. So all that does is create a vector, RPM, which has X, Y, and Z, and Gaussian point 1, Gaussian point 2, and so forth. All right? So you can write your own code and do it differently, or you can use this if you want. That just gives us the RPs, right? What we need, RPM means RP minus. What we need is the rows. So to get row vectors, we take RPs and we subtract the free vertex, V minus, this V minus. All right? So this is V minus here. We do rep mat to make it in, repeat that vector 3 times, and then we subtract all of the RPs from that simultaneously. It's a compact way to do all of this. All right? Probably the first time you write this code, maybe you can do it your own way, like directly with a for loop or something, or you can try to understand these matrix operations. All right? Okay. So we create row M plus, and row M minus, which means we get all of these vectors, right? By doing all of that. Okay, good. Any questions? All right. Now we have to do the same thing. So this is continued code, right? So this is continued code from the previous slide. So in the previous slide, we looped over the testing functions over M, right? And then ... and then we continue here. Now we're going to loop over in the inner for loop, we're going to loop over the basis functions, n's, and we're going to do the same thing. But now we call these Vn. So we have V1n and V2n and V3n. So here's the source triangle now, which has Tn. The previous code was the observation triangle. And these are all Qs now, right? RQ1, RQ2, RQ3. And these are all n's, all right? But it's the same exact code. Then you get to this point, all right? Now, what you do is okay, so first you need to calculate the distance between the two triangles because you have to have a switch between far terms or self terms in the impedance matrix, right? So we have to check if we're going to have to calculate a self term or a far term. So what we do is we calculate the centroid of the two triangles, right? The two triangles we're going to consider first are the minus and minus. All right? So the centroid of Tm minus and the centroid of Tn minus are here. So we take the sum of the 3 vertices and we multiply by 1/3, right? Same thing as a 1-point rule. Then we check delta centroid, which is the distance between, which is the Euclidean distance, square root of x minus x prime squared, square root of y minus y prime squared, and so forth, of the two centroids. All right? If that delta centroid is less or greater than the near distance, which means that it's not a self term, then we calculate RPQ next. So this is another way to do everything simultaneously. It's a function called p distance 2. You feed it 2 lists of points, and it calculates the Euclidean distance between every combination of those 2 lists of points. So it gives you RPQ. Then we have this. Here's our Tm minus, Tm minus. Let's go back. This is the Tm minus, Tn minus. So we need Lm, Ln over 4 pi. Don't forget that. We need the weighting coefficients, and we multiply this double summation for these weighting coefficients to rho m minus, dotted with rho n minus, and then we have minus j omega epsilon, j over omega epsilon, and e to the minus j k rpq over rpq. All right? So remember that. And we'll go to here, and we'll see that that's exactly what we're doing. Double summation, sum, right? Lm Ln over 4 pi. That was the coefficient out front. Quadrature rule, all rows column 4 is the weight coefficient column. for the observation and all rows column 4 for the source quadrature rule. So we get the weighting coefficients for the observation and for the source, and we multiply those two together first inside of these two sums, and we multiply that result by j omega mu over 4 times rho m dotted with rho m minus, rho n minus dotted with rho n minus, right? Then we have minus, because it's a minus minus, they have the same, they're on the same sides of the basis functions and testing functions. And then we have j over omega epsilon, and then we have e to the minus jk rpq over rpq. That's it, right? That's the whole calculation.
What was the near distance again?
So we looked at this last lecture. Near distance is some kind of number that you set in your code. For now, it's some multiplicative factor of the average of all the lengths of the edges. Or you can set it directly to lambda by 10. You have to choose some clever thing here. So if delta centroid is less than, the reason why we try to do the average of all this, the average edge length in the mesh, is because if you have very small triangles that are, trying to resolve some kind of current that's varying a lot, then you might, lambda by 10 might be too big, right? So if you use the average edge length, then maybe that will give you a better indication, right? Okay, good. So, all right, if you guys understand this, then that's great. You'll have to understand it because you're going to write your own code. All right? Good. All right. Okay, so that, and then you repeat this calculation. So then you repeat this line of code for the other, the Tm minus Tn plus, the Tm plus Tn minus, and the Tm plus Tn plus. All right, and then you add all four of those together and load it into the Z. Mn equals to, Tm minus, Tn minus, dot, 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 and add all three of these, right? And you add all those up and you put them into this. Then you change n and n, or n and m, in these two loops, right? The n is the inner loop and the m is the outer loop, and you calculate all of the impedance matrix. Yeah? Good. Okay, great. So that is everything for the far distance terms, right? Which are usually the easier ones. Now we have to get into some new theory, I suppose. Not new theory, but how do we calculate the self terms, right? And the self terms are going to require us to understand a few things. So we're about to launch into that, all right? Any questions on this first? All right. So let's launch into the singular matrix elements. How do we calculate this self term? So here's what I'm showing is two edges, edge M. Oh my goodness. I'm showing edge M here, which is this edge here. So that means it has this triangle and that triangle, right? And edge N, which is this edge here, which has this triangle and this triangle. That means that this triangle here belongs to both the testing and the basis functions, right? Okay, so that means those triangles overlap. And when we do the Gaussian quadrature integration of, this will be the, let's see, this is the edge M. So it's rho M minus. So this triangle is the minus triangle of edge M, and it's the minus triangle of edge N. So that means when we do Tm minus Tn minus, we're going to have to use singular matrix approaches, all right? Self terms. So when R and R prime are close, in our code we measure the closeness as some scalar coefficient times the mean edge length, or the distance between the center of the triangle delta RC is less than some constant A multiplied by the average edge length in the whole mesh. The singularity must be extracted from the Green's function. It's a Green's function that becomes infinite, right? When the source and observation point approach each other. So what do? We rewrite the Green's function as, so it's e to the minus jkr. We rewrite that as e to the minus jkr over r. We add and subtract the same term from it. Plus 1 over r, minus 1 over r, right? So that means this equality is upheld. If you add a constant and subtract it, then it's the same function, right? So the reason why we do that is we subtract out the singularity from e to the minus jkr over r, and that becomes a well-behaved function that can be integrated. As a matter of fact, if you take the limit of e to the minus jkr over r minus 1 over r as r approaches to 0, then that equals to minus jk. So you avoid the singularity altogether. All right? In that term. So we remove the singularity from the first term, and we can integrate this numerically using Gaussian quadrature, any terms involving that. Now, then we just have to deal with this singularity, the 1 over r term, we have to handle separately, and we're going to do that analytically. All right? Okay, that's a strategy. Everything I'm about to show you is in this paper by Rao, Wilton, and Glisson, the RWG guys, who have this paper, which is highly cited, in 84. All right? And it's called Potential Integrals for Uniform and Linear Source Distributions on Polygonal and Polyhedral Domains. All right? Okay, so here is our integrals, all four of them. We have plus and minus here, right? All four of them represented with pluses and minuses, then you have a plus minus there. That was the only difference between the four combinations, right? Okay. So, and you'll notice that before we use Gaussian quadrature rules, where we have to multiply by the area. So let me show you that. Where was that? The Gaussian quadrature integration. This rule involved multiply by the area, right? So if you look here, we had the areas in the denominator when they were integrals still. When they become summations, the areas are gone because we multiplied by the areas of each of the triangles as part of applying the Gaussian quadrature rule, converting the continuous integral into summations, and therefore those areas canceled. All right. So if we look here, we still have all of the areas because they're still integrals, they're not summations yet. Okay, good. So all we do to get to this step is take our original integrals, and we had just e to the minus jkr over r on the outside, right? But now we've subtracted 1 over r and added 1 over r. That's the only difference between what we had before and this. So plus 1 over r minus 1 over r, right? All right. Now what we do is we have three terms. We have this whole coefficient multiplied, FOILed into this, e to the minus jkr over 4 over r minus 1 over r. So that's term 1, we call it. Then we have all of this multiplied by 1 over r, but we're going to do that two separate terms. The first one's going to be all of this multiplied by, or sorry, not all of that. This part multiplied by 1 over r. Then the second or the third term will be this part multiplied by 1 over r, or sorry, this 1 over r. This and this, right? So there are three terms that come out of this, and we add them all together. The first one is this whole part, right? We evaluate that numerically using Gaussian quadrature because we know it has a well-behaved limit. Then we have two terms. We have the second term here, which is the vector potential term with the 1 over r, and the scalar potential with the 1 over r. All right? Okay, good. So what you notice about these two terms is that this is linearly varying because rho varies linearly. So the current on this varies linearly. We have to integrate a 1 over r singularity for a linearly varying function. This one is all constants, right? So this one is constant. We have to integrate a 1 over r singularity for a constant source distribution. So you'll see that we're going to break this into two things. We have uniform source distribution, that's what's associated with the third term, with the scalar potential, and linearly varying source distributions for the first term, right? All right, so that's what we've done here. We've broken this into three different terms, right? 1, 2, and 3, and you add them all together. Strategy is going to be evaluate the first one numerically, completely. The second one, we have an inner integral and an outer integral. The inner integral is over the source, given an observation point, passed in from the outer integral. So that's kind of how these double integrals work, right? We have to understand that. When you integrate the inner integral, you're just assuming that this r is some value. The integration variable r prime for the inner integral does not depend on r. So it's a constant with respect to the inner integral. So that means when you do this integration, you can treat this r as a single point, some variable point, right? It's a variable, but it's passed in from the outer integral. And it's not an integration variable, so we can just treat it as a constant. And then we perform the inner integral as a function of this r, because this r is passed in from the outer integral. All right? So you got to think of it like that. We're going to do the innermost integral analytically. We're going to derive the formula for that. And then the outermost integral using Gaussian quadrature. And same thing for this one. Innermost integral analytically, outermost Gaussian quadrature. The formulas we're going to use are here, which is, so we have two types of integrals that we have to be able to evaluate analytically. Analytic integration is going to be this inner integral here. And then we do Gaussian quadrature on the result of that. Same thing here. We do analytic in here and Gaussian quadrature out. All right? So we need to understand these two integrals. I've broken them into two types, type 1, type 2. Type 1 is the vector potential integral with a linearly varying source. And type 2 is a scalar potential integral with a constant source. All right? And they both have the 1 over r singularity that we have to treat analytically. All right?
In the first terms,
Well,
how do you like solve that numerically?
this one and this one?
Yeah.
So the first one, remember, because we subtracted out the singularity, minus 1 over r of the Green's function, this can be fully integrated numerically, right? There's no singularity to worry about. The second term has the 1 over r, which came from the vector potential foiled to the plus 1 over r. That term cannot be evaluated numerically completely because we have to treat this 1 over r singularity. So that we have to do analytically, the inner integration, and then we can do the outer one numerically, given the analytic integration result for the inner integral as the integrand of the outer integral. All right, good. Type 1 and type 2, so let's launch into it. So first thing to do this, we have to understand some particular geometry. Big picture, what these guys did in this paper, the Rao, Wilton, and Glisson paper, what they did in this paper is they converted the integration over the area of the triangle. So that's the problem, right? The observation points and the source points coalesce by inside the area of the triangle, inside the interior. They converted the integration over that area to a line integral around its perimeter. What does that remind you guys of, first off? Here's a triangle. We're going to, instead of integrating over the whole area, we're going to convert that integration from an area integral to an integral around its perimeter. What does that remind you of? Very nice. Very good. But it's a surface divergence theorem. So that's the big picture. That's the idea. Use the surface divergence theorem to convert the area integration to an integration around its boundary, right? Good. So that's a big picture. But to do that, we need to understand how to parameterize the sides of the triangle so that we can integrate around them. And to do that, we use this following geometry. All right. So consider a line segment. Here's a line segment. This is the segment, this dark line here, okay? Consider a line segment, C. So we call this line segment C. With endpoints, okay, so first let me describe the observation, or the coordinate system. Here's the origin, O, of the global coordinate system. There's a position vector, R, which points to the observation point, right? There's another position vector, R prime, which points to the source point, all right? Then we have the projection of the origin onto the plane S, which contains the triangle. Call that O prime, all right? So project the origin down to the plane of the triangle, and the same with the position vector R, now becomes rho. R that's projected in the plane of the triangle becomes rho, and there's a distance d, which is the height of the observation point, off of the triangle, plane of the triangle, right? Just D. Okay, so the position vector observation R becomes rho in the plane of the triangle, and the position vector, the source position vector, the prime vector, R prime, becomes rho prime in the plane of the triangle. All right? Okay. Now, we have the source segment C. The projections of the source and observation vectors R prime and R onto the plane of the polygon are rho prime and rho, respectively. All right? Okay. We're going to need all these different quantities here. And first thing is, the line segment C has endpoints. So it has endpoint L minus, endpoint L plus, all right? And I'll explain what L is. First off, there's a right-handed coordinate system here like this, all right? Here's some coordinate, and then here's another one here, okay? And they're right angles. That's why there's a right angle symbol here. So what this means is I can parameterize this line segment L in this coordinate system, which has this coordinate P naught, but don't worry about that, and L as a variable, which takes you from L minus to L plus, all right? So that's the idea, and let's see how you can do that. So the vector that matters for us is what? Is the vector from the source observation point to the, or source point to the observation point, right? So that is this vector here, P. So here's P, all right? P is the vector that matters. Normally it's R minus R prime, right? So it's this vector here, right? And we call this R, capital R. But now the same vector projected in the plane of the triangle is P, yeah? Okay, so, and we're always going to be doing calculations of the plane of the triangles, right? There will never be an observation point above the triangle because it's method of moments. We put the points of observation on the triangles in the mesh for the testing function, and the points of observation on the triangles in the mesh for the source function, right? All right, so this point P, this distance P, can be parameterized in this coordinate system as the following. Let's see where P is. P is capital P, right? Capital P here. So, okay, so this is how we do this. First, we have rho plus or minus. So rho plus or minus are the vectors which point to the endpoints. Rho plus and minus, R plus or minus. Okay, let's see, R plus or minus. Oh, no, okay. So this is just this vector rho, and that's just that vector rho, right? What we're doing is we're subtracting off the normal component. So we're projecting it into the plane of the triangle, right? That's this vector and this vector. I don't know why I call it plus and minus yet. Maybe it's plus and minus triangles. All right? Okay, L hat is a unit vector in the direction of the line source, or the line segment, right? So that's nothing but rho plus minus rho minus. Oh, so, okay, it should be capital P probably, but here's rho, okay, it's not shown in this drawing, that's why. Rho plus points to the, this is rho minus, points to L minus side of the line segment, and rho plus points to the plus side, L plus side, all right? So if you subtract those two vectors, what do you get? So this vector, these two vectors, if you subtract them, then and that means you flip the minus triangle, so now the minus triangle, or sorry, the minus vector points that way, and then you connect tail to head. So it's along the line segments, right? And then you normalize it by its own length to give you, the unit vector. Okay, now U is a vector normal U hat to the line segment, right? This vector. To find that, we take the cross product of L and the normal. The normal is the normal to the plane containing the triangle. Make sense? Because L crossed with N gives you U. Yeah? All right? L plus and minus are the coordinates in this L in this L coordinate system, and this coordinate system here. In this coordinate system, L measures from this origin. L minus is the length L measured along L hat from here to here, right? L minus is rho plus or minus minus rho. So here's rho, points to the observation point. Rho plus or minus points here, let's say rho minus. And we dot that, so that's going to be this vector, right? If you subtract them, and we dot that with L hat, which means we take this vector here has these components, right? Has this component and this component. This vector does, right? So if we take the dot product of that vector expressing these two components with L hat, then we pick up this vector only. And the length of that vector is obviously L minus, which is the length of L, the coordinate L. It's the coordinates of this endpoint of the segment in the LP coordinate system, or measured from the origin of that rectangular coordinate system, right? Orthogonal coordinate system. Okay, all right. And then you can do the same thing with the L plus. So you get L plus and L minus, the L coordinate of the beginning and the end of the line segment. P0 now is nothing but rho plus minus rho. So here's rho plus goes to here. Rho plus goes here. Minus rho minus, which is this one, gives you this vector. Or no, minus rho, I'm sorry. So let's say rho minus. Rho minus minus rho, here's rho. If you subtract those two, you get this vector here. And you take the dot of that with the u unit vector. Means now we want this component, right? Instead of the previous calculation was this component of this vector. So that gives you P0, the distance from the observation point in the plane of the triangle to this kind of origin where we're measuring L from. All right. And you can do the same thing for the other side. P0 hat is unit vector in that direction. That's this unit vector. And R0 is nothing but the P0, so the square root of this. So here's R0 right here. All right, so you just add the vertical distance D. That's R0, here's D, and here's P0, right? So it's the length of, from the actual observation point not projected down, which we will never have because D will be 0 to this point. So that means R0 will equal to P0, all right? Always. And then R plus or minus is the square root of P plus or minus squared. So here P plus goes from the observation point to the, P minus goes there, P plus goes here, all right? This says P plus, this says P minus, all right? And that's it. So, okay, so those are geometrical quantities. We need those to understand how to apply the rule that we're going to do next, okay? Rho plus and minus are not shown in the figure, but they point from the origin. Anything that's rho is in the plane of the triangle. Anything that's r is includes the observation point above the triangle, right? But that'll never happen. So rho's and r's will always be the same. But rho plus and minus points from the origin in the plane of the triangle to the minus edge. That's rho minus. And rho plus goes to here. Okay?
Where are the triangles?
So, good question. This is one side of a three-sided triangle, this side. So it could be here. It won't be there, because these things always point outward. So it'll be there maybe. And all three of those sides are in this plane S. All right? Okay, these are, you take some like looking at them and trying to think about it, okay? So let's start with the first term. Why is it not letting me do the erasing? Okay, can't erase that. I don't know why. All right, uniform source distribution. So what are we showing here? A uniform source distribution. That means that everything under the, or everything in the integrand is, you know what, let me see if I can somehow, let me do this. If I discard and I start again. Okay, so this source distribution now is uniform, right? This is the scalar potential term. This current J here is uniform, right? And here's that edge I was talking about. Here's an edge. Here's the unit vector u normal to that edge, right? It's always an outward normal. Here is the triangle area S. And here is the boundary of S, which is partial S. And here is R prime, for example, and R, 2 points in the triangle, because it's a singular term. And we have the normal to the triangle, all right? Okay, now, the potential due to a uniform line source S can be written in the following form. So here's where we apply the surface divergence theorem. 1 over R ds prime. This is the integral we're trying to solve over some surface S. There are some coefficients out front that we're not considering here, but we'll multiply them back in later that were associated with the uniform source, right? Remember, just as a reminder, that was part of this integration right here. This is the type 2 inner integral, type 2. And the type 2 inner integral is nothing but this. So it's just 1 over R, these coefficients come out, right? Okay. Okay. Whoops, here. All right, so 1 over R ds, we can write that as the limit as epsilon goes to 0 of S minus S epsilon. What do we have to do there? In order to apply a surface divergence theorem, then the function that you're applying the surface divergence theorem has to be continuous within the domain. So if you apply divergence theorem to a sphere, then the vector field has to be continuous inside of the sphere to apply the divergence theorem and convert it to a surface integral on the surface of the sphere, a flux integral through the surface of the sphere. All right? So in order to kind of make that a continuous function, we subtract out the observation point, a small circle surrounding the observation point of radius epsilon, right? And it's not continuous there, right, when the observation point goes, or source point goes there. So we remove that by doing S minus S epsilon. Well, here's S epsilon, right? And here's S. All right. And we take the limit as epsilon goes to 0, so that point shrinks around that point. And we can say that 1 over R is the divergence S surface divergence prime of the function R over PP hat. Remember, P is here. Rho minus rho prime, which is our R, right? R is R minus R prime. All right? Plus this term. Now we had to, okay, so the integration over S is now S minus S epsilon and S plus S epsilon. All right, so don't worry about this term here. We're going to show that it goes to 0 anyway. All right? The whole point here is 1 over R becomes divergence of R over P hat, and we'll derive that next slide. All right? Surface divergence theorem. And now, of course, this is over, we can use, okay, we haven't applied the surface divergence theorem yet. We've written like this, so we can integrate the divergence of some function. Then over the triangle's domain. Then we can use the surface divergence theorem to convert the integral of the divergence into a flux integral of the flux of this function, R over PP hat, through the perimeter of the triangle. All right? So first you have to understand where this comes from. So how do we do that? So how do we express 1 over R in terms of surface divergence? So here's R equal to R minus R prime, or R prime minus R, rather. Is it supposed to be R minus R? R prime minus R. Okay. Here's R. So capital R is X prime minus X, Y prime minus Y, Z prime minus Z. All right. Okay. Same here. This is Y prime, this is Y. And P, remember, is nothing but in the plane of the triangle, yeah? Okay. And now, we can write this as, what is the divergence of the surface divergence of R over P into P hat? Well, let's calculate that. we can write the surface divergence operator as only x prime and y prime derivatives. And here's our function r over p squared p hat, or no, r over p squared p vector. All right, so that means that we've unnormalized the p vector, right? Okay, well, let's substitute in what we have for our p vector, which is x minus x, and x prime minus x, x hat, y prime minus y, y hat. All right. Now, the next thing we're going to do is we're going to do this dot product here. We're going to FOIL it out. So we have x minus x prime times partial x x prime into r over p squared, right? So all we did was the dot product first. Plus y prime minus y into partial by partial y. What I'm trying to understand is why that derivative with respect to x prime. Oh yeah, the derivative with respect to x prime is 1, right? Okay, so here we have the derivative with respect to x prime of r over p squared x prime minus x. This dot product of this x hat and this x hat will be this will be the only thing remaining, right? That means that we have, then we use the product rule on that. So here, look, this multiplied by all of that is partial by partial x prime into r over p squared x prime minus x, right? Now we use the product rule, so we call this f and this g. So g x prime minus x times f prime partial over partial x prime of r over p squared plus f, which is r over p squared, times the derivative of g prime, which is just 1. So here's g times f prime plus f times g prime. And the same thing for the other term. All right. Now, and the next step, what we do is we rewrite r here. So where's our r? R is here, right? So r is this thing here. And we have r over p squared becomes x minus x prime over r. All right? And that's because we're differentiating now. We're differentiating. So basically we perform this derivative here, which means that that's the result of calculating that derivative. You have to write it all out, okay? But that's the result of applying that derivative. All right, good. Then, same thing with the y term. Then we get here, x minus x prime squared over rp2 squared, or rp squared, plus r over p squared, and so forth. And if you add all that up, then you get 1 over r, which proves that 1 over r is equal to this. Okay? All right, good. So let's now use that. And so here we are, back to what we had. 1 over r integration over the surface is written as the divergence, right? Now we apply the surface divergence theorem. So instead of integrating over the domain S, we're going to integrate over the partial domain of S, right? That partial means the boundary. So this means boundary, all right? And it's just this function now dotted with u hat, which is the outward normal of the line segment of the triangle, right? And then dl prime, now we're integrating with respect to this coordinate along the L hat unit vector direction with respect to this origin. All right? Okay, plus the integration, this integral becomes this following expression. All right. So that is equal to, now we're going to take this integral and we have to break it into 3 segments of line because a triangle has 3 sides. There's always 3. So we sum over the ith side. This is the ith line segment. Then you have another one and one like that, right? So we're going to sum over all 3 of those sides. And this term comes from this integral. All right? Then we substitute in what all these unit vectors are. We know what u hat is. We know what p hat is, sort of this vector. And we integrate 1 over r d squared over p squared r, where d is this distance d, and so forth, right? So substitute all of that in, and someone's integrated this in that paper, and you get this following key result here. All right. So that means that the following integral identities were used to come up with this expression, all right? So this alpha from this term becomes these two tangent functions, right? So it didn't go to 0, as a matter of fact, we needed that. All right. Okay, good. So you get this result. That's all that matters. So now you have to implement that in order to calculate this integral. All right. So remember that key result. Let's do the other one now. The other one is the integral of type 1 vector potential linearly varying source function now. So this function now varies linearly over the domain of a triangle. And we have this type of vector. Let's understand where that comes from. So if we go back to here, we have rho m dotted with rho n 1 over r, right? So what we're saying is, okay, good. Let me where is it? Here. So what I'm gonna say about this is just the inner integral first. All right, so it's just the rho n. But we're gonna rewrite rho n in terms of rho prime minus rho. And I'll show you why we do that and how we do that. All right. So for now, what we're going to say is, let's just evaluate this integral and then we'll relate it back to the one that we need to solve. All right. Okay. So rho prime minus rho over r, we can write as using the divergence, surface divergence theorem, plus this term, right? And then applying the surface divergence theorem, we end up integrating over the boundary now of ru dl prime and this. And that can be evaluated by summing the three sides of the integral, three sides of the triangle, and you get this key result, okay? I'm not gonna go into depth on how to calculate that, but this is the result of it. All right, good. So we have that key result. Now we come to how we evaluate our integrals, right? So we had type 1, which is rho n dot with rho n 1 over r, and type 2, which was the 1 over r. The vector potential is type 1, the scalar potential is type 2, okay? How do we do that? First thing, and we have a result for an integral that looks like this from the last slide. So we need to rewrite our integrals in that form. So take the innermost integral and we rewrite the rho n plus or minus of r prime like this. We say rho n minus is equal to rho prime minus rho n, where rho n is the free vertex, I think. Or no. What did we do here? Rho n is still there. Excuse me 1 second. Geez, I keep coughing. Okay, rho n minus is the minus side, for example. Well, that's just equal to rho prime minus rho n. And rho prime is the actual point, the source point, and rho n is the vector itself, I believe. And then we can write that as rho prime minus rho plus rho minus rho n. And if you do this, you get minus rho plus rho, and you just get rho prime minus rho n, right? So rho, okay, this is what it is. Rho n minus. So here's a triangle. Here is, we're calling this rho n. All right, so it's a different nomenclature, I guess. And then there's a rho vector here, which is the position vector to the source. Then this vector here is rho n minus, right? Okay, so you subtract those two. And so rho n minus here is rho prime minus rho n. And then that, all we do now is we add minus rho and plus rho. So does it make sense now? We have, so then we subtract rho and add rho. Subtract rho and add rho. All right? Okay. Now, okay, so if we take this integral now, and we replace the rho n with this expression here, then this becomes these two integrals. All right? Oh my goodness. becomes these two integrals. Rho minus rho prime over r, right? That's this. That's the first one that this integral is breaking into two terms, this term and this term. This term and this term, by the way. And plus the rho minus rho n into just 1 over r. Is that clear? So this integral we called I1, but now we're going to call this first term that I1 breaks into I1 prime. And the second integral that it breaks to into I2 prime. All right? Okay, why do we call this one I2 prime? Well, because if we look here at our type 2 integral, which is our scalar potential integral, we're going to solve the innermost integral analytically and using the I2 prime that we solve for here, right? Here's the I2 prime. That's I2 prime. Remember, this was one of our key results. So this is a function of the observation point. And we're going to substitute this expression here in for this entire integral. And then we just have to integrate that over t and dr, right? So we'll see how to do that. Okay, but this integral is the exact same as this one, right? So somehow we have the result that we had for our scalar potential integral we called I2 can be reused in our expression of I1 in terms of I1 prime and another term. So we can reuse that here, right? So we just have two formula, I2 prime, and I1 prime. Here's I2 prime, here's I1 prime. We solved these in the preceding few slides, yeah? Okay, good. So let's see some code to do that now, yeah? Okay, so here is our singularity extraction led to three terms for each of these, right? For example, for Tn minus and Tn minus, we have term 1, term 2, and term 3. Actually, this is for all of them, right? So they should say Tm, oh my goodness, gosh. Tm, oh my goodness. As soon as you touch it, it just plus minus, all right? So this integral broke into three terms by using the singularity extraction or subtraction. We subtracted the singularity and added it back. That resulted in three terms. This becomes three terms, right? And these three terms we attacked in different ways. First one, completely Gaussian quadrature. Second one, innermost integral analytically, outermost Gaussian quadrature. And the third one, innermost analytically, outermost Gaussian quadrature. But these two result in I1 prime and I2 prime and I2 prime again. All right? So the code is here. Here's term 1, term 2, and term 3. All right? How do we calculate term 1? First, we calculate RPQ. So this else statement comes from, you remember in the previous code where we had, there was an if near distance, right? So here's the impedance matrix fill code. We start with looping over M, then we said dot, dot, dot. And then we went to looping over, so dot, 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 looping over N. And we had if delta centroid is greater than near distance. The else statement, which is going to go after all this code, dot, 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 right? Dot, dot, dot brought us to here. So here we have dot, 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 right? So here's the else of that if near distance is greater than, or if delta centroid is greater than near distance. So RPQ, we have term 1, term 2, and term 3, which is this term, and this term. And term 1 is nothing but the double sum, Lm, Ln over 4 pi. Then we have, quadrature rule observation, quadrature rule source, the weights, j omega mu, rho and minus, and then the same thing as we had before, except now e to the minus jkr becomes e to the minus jkr over r minus 1 over r. And I have this function called get Green's function non-singular part. Why do we need that? Because it looks like this, because we have to manually implement this limit. So I just have a function here. I pass it the RPQs and the K naught. I calculate e to the minus jkr over r minus 1 over r. But then I check if it's not a number because r is equal to 0, which it will be, then we know what the limit should be. It should be minus jk. So you have to manually put that in. Then we return that, yeah? And then we return that. Then we integrate that whole thing numerically using Gaussian quadrature. Then here we do term 2, and we have a function here near term inner which implements I1 prime and I2 prime for this integral. And the rest of it is dot product of rho m minus with this analytic integration I2 prime. And then the rest is integration, all right? We'll go over that next time. And then here we have near term inner for I2 prime, and we just have this coefficient out front, and then we do one summation for the outer integral. But here we have two summations because it's outer and inner integral numerically. All right? All right, we'll pick up from here next time, yeah? Okay, good.